Hello everyone, my students. Now, last video we began with optimization. And optimization is a really profound and very common type of calculus problem, very applied problem. Okay, since many of them deal with real life situations. So we did 2 of them last time. Let's see if we can do a couple more this time. So let's say we have a window. This is a really classic one. This one's a classic. Say we had a window. Okay? A rectangular window. And we had a circle. It's known as a Norman window. And we have dimensions x and y. Now, well, I'm a window man, okay? So I make windows and I'm trying to find the dimensions x and y of the window such that the area of the window is at a maximum. However, the total amount of the total perimeter that I'm allowed to use, okay, the total perimeter is 16 feet. 16 feet, okay? And when I mean total perimeter, I mean this entire thing. So with this beam included, okay? So with all the beams. Now what do you do? How do you solve this? So we know the perimeter, 16. So we know that 2x plus 2y plus, well, the radius of this is x over 2. Okay, since it's a semicircle right on top of it. Plus pi 2 pi r. So 2 pi times the radius, so pi x must equal 16. Or we could write pi plus 2 times x plus 2y equals 16. Okay. Now we want to maximize this area xy plus pi x squared over 4, okay, pi r squared, divided by 2. It is a semicircle after all, okay? And this is important, okay? Because it's a semicircle, so this also has to be divided by 2. So this is divided by 2. Okay, so we have pi r, 2 pi r over 2. Okay, it's a semicircle. So the circumference is of a semicircle. Semicircle, pi r squared divided by 2, semicircle. We have the area of a semicircle. Okay, so that gives us xy plus pi x squared over 8. Okay, so pi x squared over 8. Now, what does that mean? Okay, for us, it means that our best bet is to solve for y and replace it with x, because we have so many x's here, and we have an x squared, which we really don't want to disturb unless you want a nasty equation. So what do you do now? Well, 2y equals 16, okay, so what I would do, preferably, is we have 2y equals 16 minus pi plus 4 over 2. I'm just combining that little fraction term over there. And we get y equals 8 minus pi plus 4 over 4x. Okay, now let's substitute this into here. So we have area equals x times 8 minus pi plus 4 over 4x plus pi x squared over 8. Okay, so we have 8x minus pi plus 4 over 4x squared plus pi x squared over 8. So if we were to combine these like terms, you would get area equals 8x minus, well, this, if we were to turn this into a common fraction with 8, denominator 8, we have 2 pi plus 8 over 8, okay? So we have pi x squared over 8 minus 2 pi plus 8 over 8x squared. Okay. The hard part is just simplification to all the algebra. Okay? So we combine these two fractions and we get plus negative 8 minus pi over 8 x squared. Now, if we were to take the derivative dA dx, well, that equals 8 plus, or rather, yes, plus 2 times x, 2x. So we have minus 8 minus pi over 4x. We set this equal to 0, okay? Now we have 8 equals, well, if you want to take out this negative sign, you have plus pi plus 8 minus. We're basically taking out the negative sign over here. And that allows us to do 8 plus pi over 4x. So we have x equals 32 over pi plus 8. So if the beam was included, that's what we assumed, okay? If the beam was included, we would get x equals 32 over pi plus 8 meters or feet, whatever the units are. Okay? We said feet. So 32 over pi plus 8 feet. And you could easily solve for y using our little equation here. Okay? And, you could solve for it, but this is our answer. You can solve for y just by plugging into the equation. Okay, so one of the maximum base will be 32 over pi plus 8. I'm going to do another one, okay? There are a ton of these. You can make a ton of these. Now, here's another classic. Let's say you were part of a box company. And you want to make a box, okay? Out of paper, as a paper model. So the paper is 8 feet by 10 feet. Okay? So far, so good? Now, what we're going to do is cut out squares from each of the sides. This is a classic, okay? So this one's a good one. We're going to cut out squares from each of the sides. Okay? So we want to find out the maximum, the dimensions of the square. So how far should we cut so that the volume of our box that we create is the maximum, okay? So if we had our box, which looks like this, you have to imagine that it's folded upward, okay? So this, if you fold it upward, this is X, this is Y, this is Z. We get, it's not the best box, but we have X, Y, and Z, okay? So the volume of our box will be this length. Okay, let's call this X, X. So this length will be 10 minus 2X times 8 minus 2X times X. Okay? Times X. Now this one is a little bit easier than the other ones because now it's all in X. We just need to find dVdx. So why not multiply these together? So we have 80 minus 20x minus 16x plus 4x squared. Plus 4x squared. Then we have x. We multiply this by x. We have 80 minus 36x plus 4x squared times x equals 4x cubed minus 36x squared plus 80x. Now, if we take the derivative with respect to x, we get 12x squared minus 72x plus 80 equals 0. Now, if we factor out a 4 from each of these, we can solve this equation. So 4, then we have 3x squared minus 18x plus 20. Okay, and this we can solve with our quadratic formula. Okay, so negative b plus or minus the square root of b squared, so that's 324, minus 4ac, so we have 4 times 3 times 20, 4 times 3 times 20, which is 240. All that over 2a. 2 times 3 is 6. Okay, and we get 18 plus or minus the square root. Okay, we just do a quick subtraction problem here. Okay, and we get 84. Okay, so we have 84, square root of 84, which is 21 times 4. Okay, so we can simplify the radical. So we have plus or minus 2 root 21 over 6. Which means we have 3 plus or minus square root of the square root of 21 over 3. Okay, now what does that actually mean? It means that if we were to add square root of 21 over 3, well, the square root of 21 is more or less an approximation, but I would say it is a little more than 4. So we have 3 plus 4, a little bit 4 over 3 maybe. Okay, some approximation. That gets us above 4. And this is actually a problem. Because if we cut more than 4, it will be impossible to make a box since the cuts can only can have a maximum of 4 inches. Okay, otherwise you'll be overlapping into the other side and it'll be impossible to fold the box. Okay, so we have to pick 3 minus the square root of 21 over 3. Okay, or 9 minus the square root of 21 over 3. And you should have actually been doing this, but if you want to check, it's always good to check. If you want to check, you can simply use the second derivative test. Okay? Since that's usually the quickest. Okay, so the second derivative equals 24x. And this we know is greater than 0. Okay? Because square root of 21 is less than the square root of 81, which is 9. So this is less than 9. So we know it's going to be positive. So we have 24x minus 72. Okay? So 24 times this, we get 72 minus so we get 72 minus 8 root 21 minus 72. Okay, and we get negative 8 root 21. Okay, because we just, we got 72 minus 8 root 21, we just multiplied by 24. The 3 cancel, we're multiplying by 8. The top. So the 72's cancel. So you have a negative answer. It's concave downward, which means we have a maximum. So I've not been doing this for the last couple, but it is a practice that you should do always. You should always verify your answer with either the second derivative test or the first derivative test. Usually second derivative is better with these optimization problems, but the first derivative test can work just fine. So we verify that this is a maximum point. So our final answer, you need to cut 9 minus the square root of 21 over 3 feet. And we are done. I think we can do one more. And this one's more of a graphical problem. Okay. So let's say we had the graph of the circle. Or actually, let's have a graph of a function, not a circle. Okay? Just given the time constraints. I mean, you could do this with a circle as well. But just due to time, you can do an easier function, slightly easier. It's not easy still. Okay? And let's have f of x equals the square root of x. Okay, so you have 0, 0, 1, 1, 4, 2, so on and so forth. Okay. Now, given the point 2, 0, what is the closest point? X, y is the closest point to the point 2, 0 on the graph of f of x equals square root of x. Okay? So we want to find the closest point, the points on the graph of the function, which is closest to the point 2, 0. Okay. So we want to minimize the distance we'll call d. Okay? And we use distance formula. y2 minus y1 plus x2 minus x1. Doesn't really matter the order. Okay, so we have square root. So y2 minus y1 squared plus x2 minus x1 squared. Okay. So you have x minus 2 squared plus y squared. Okay. Now, this is actually quite a challenging thing to differentiate. Okay? But before we do any differentiation, we gotta get rid of one of these variables. So why not we get rid of y? Because we have y squared, because the square root of x is very convenient, and we don't want to mess with replace x because we have this nasty squared expression which will result in another y squared. So why don't we replace y equals square root of x? Okay, since the point is on the function. So we have x minus 2 squared plus x. Okay? Now here is where a little insight comes in. Okay? Now, if the distance is a positive value, distance will be a positive value. So that means the radical we're talking about will evaluate to a positive real number. Okay? So if the distance is a positive real value, then in order to minimize this distance, we have to minimize the value inside the radical. Because if we're dealing with positive real numbers here, that means the smaller the value in the radical, the smaller the actual radical expression, right? Because we have smaller, 1 is smaller than 4, that means square root of 1 is smaller than square root of 4, which is 2. So this is true for all positive real numbers. So why not we just minimize this expression? Okay? So we have dd. Okay, I really shouldn't have picked d for that, but okay, dd to dx, dd dx. Okay, and we're going to take the derivative of this function. So that's 2 times x minus 2, it's chain rule, times 1, so it doesn't really matter, plus 1 equals 0. Okay? Now, we have to solve this for 0. So 2x minus 4 plus 1 equals 0. So you have 2x minus 3 equals 0. So that gets us x equals 3 over 2. And let's verify this, okay? And since the derivative is a linear expression, it's going to be really easy to find the second derivative. So you have d squared d over dx squared, okay? So that's 2x minus 4 plus 2x minus 3. So this will just be 2, right? Derivative of this is our first derivative. Taking the derivative of that will get you 2. So that means it's always concave up. So x equals 3 over 2 is a minimum value. Okay, second derivative test. So we didn't actually need the number line. Okay, we just need to find d squared d over dx squared. Okay, so bye-bye number line. Now, let's find our y coordinate, okay? So y, or f of 3 over 2, is square root of 3 over square root of 2, which is equal to the square root of 6 over 2. So the point on the graph closest to the point 2, 0 is 3 over 2, comma, root 6 over 2. And we're done. Finally done with this kind of horrific problem, but it was not that horrific. But optimization problems can get really messy sometimes. But if you know how to set up the problem, it's not bad. And just for some perspective, I would say the maximum point, our point is here. Right here. This is the closest distance. And we're done.